But here's where we really want to go with this, which is how do you find the derivative of an inverse trig function? So the way to do this is to know a little bit about inverse functions and a little bit about implicit differentiation. And once you do that, it's actually not that hard. Or actually, I'm going to say you have to know three things. You have to know about inverse functions. You have to know about implicit differentiation, and you also have to know about trig identities. You can't really ever forget the trig identities in this course, or the next course, or the course after that, really. So anyway, first of what we know about inverse trig functions. If y equals arcsine of x, we can rewrite that as x is equal to sine of y. I mean, that's sort of what it means to say that y is the inverse of the sine function. So if y equals the inverse sine function of x, then x equals sine y. So now we're going to go to point number 2, which is we're going to differentiate both sides using implicit differentiation. The derivative of x is 1. The derivative of sine y is cosine y, but not quite, because it's y and not x, which means that we then have to multiply by the derivative of y. So that's going to be y prime. So it's cosine y times y prime. We can now solve for y prime in terms of what we have here. We can say y is equal to 1 over, sorry, y prime is equal to 1 over cosine y. Now, cosine y, there's an identity that I've mentioned is very important, which is cosine squared x plus sine squared x equals 1. That gives us that sine squared x, or in this case, let me write it for cosine x. That means that cosine squared x is equal to 1 minus sine squared x, and that cosine x is equal to the square root of 1 minus sine squared x. So this is equal to 1 over the square root of 1 minus sine squared y. Now why does that help? Well, because we know that sine y is just equal to x. So that means that y prime is equal to 1 over the square root of 1 minus, I replace sine y with x, and I just get 1 minus x squared. So that is, in fact, the derivative of the arcsine function. The textbook has a list of what the derivatives of all 6 inverse trig functions are. However, I've put up the 3 that are the most common that you should actually know. The derivative of arcsine is 1 over the square root of 1 minus x squared. The derivative of arccosine is the same thing multiplied by -1, so it's -1 over square root of 1 minus x squared. And the derivative of arctangent is 1 over 1 plus x squared. There's no square root in that. The derivative of arctangent actually is an incredibly important function. It comes up a lot in Calc 2. You should know all of these, but it's especially important, I think, just because it comes up so frequently, to recognize that that this is the derivative of arctan. So what we want to do now is do a little bit more complicated example of how to find an inverse, of how to find a derivative of an inverse trig function. So we have here the arcsecant function, and by the way, I've put up here the graph of the arcsecant function. This is y is the arcsecant of x. So in order to find y prime, we're going to do is use implicit differentiation in much the same way that we did with the arcsine function. So if y equals arcsecant of x, then that means that x is equal to secant of y. Using implicit differentiation, we take the derivative of both sides. The derivative of x is 1. The derivative of secant y is secant y tangent y. You should remember what the derivative of the secant function is. But since this is y, we need to take that and multiply it by y prime. So now we can solve for y prime in terms of what we know. This is going to be y prime is equal to 1 over secant y tangent y. So first of all, we see that x is equal to secant y. So right away, I can just replace this with 1 over x times tangent of y. Now, how do we find what tangent y is in terms of x? What we need is the identity tan squared x equals secant squared x minus 1, or certainly by extension that means that tan squared y is equal to secant squared y minus 1. So I can replace this, right? This is 1 over x times, I'm going to write plus or minus the square root, just for the time being. This would not be a complete answer, but if tan squared equals secant squared minus 1, we don't really know whether tan is the positive or negative square root of that, so I'm just going to write that it could be plus or minus secant squared y minus 1. Fortunately, we can replace the secant squared y with just x squared, because x is equal to secant y, so this is going to be 1 over x times plus or minus the square root of x squared minus 1. Now, question is it plus or minus? Well, this is one of the reasons I put the graph of secant, I put the graph of y equals secant x up. If x is a positive number, in other words, if x is this branch of the graph, then what we can see is that the angle, y, is between 0 and pi over 2. And we know that for angles between 0 and pi over 2, tangent is a positive number. So if x is greater than 0, technically it'd be greater than 1, but the point is if x is positive, then tangent, if x is positive, then tangent of y is greater than 0, because any angle in the interval 0 to pi over 2 has has a positive tangent. On the other hand, if x is negative, in other words, if we're talking about this branch of the secant function, what we can see is that we get an angle in the range pi over 2 to pi. So angles between pi over 2 and pi have a negative tangent. So what that means is that for angles in this range, the tangent is positive, and for angles in this range, the tangent is negative. But when we're in this range, which I'll label with a 2 for the second range, and I'll call that this the range 1, we already have a negative value of x. So what that means is that we'd end up with a negative x times a negative tangent would give us a positive number. And of course, if we're in this branch here, a positive x would give us a positive tangent. So once again, x times tangent y would be a positive number. Therefore, the way we're going to resolve this is we're simply going to write y prime is equal to 1 over the absolute value of x times the square root of x squared minus 1. In other words, this product here is either going to be negative times negative or positive times positive. So we're just going to do something that ensures that this entire denominator is positive. And what we do is we take the absolute value of x, and then the square root of this expression is already going to give us a positive number. So this is what we consider to be the derivative of secant, not just consider, this is in fact what the derivative of the arcsecant function is. Let's just do one more example that we can't get an answer to from the book. So let's suppose y equals arctangent of 5x, and the problem is to find dy over dx. One thing you could do is you could simply take note. You could simply do this by the chain rule, since the book has the derivative of arctangent. But sometimes, for example, if you're explicitly asked to do so on, let's say, a test, you might have to show that you can do this by implicit differentiation. So let's do our normal thing. If y equals arctangent of 5x, then that means that 5x is equal to the tangent of y. So if 5x equals the tangent of y, then let's differentiate both sides. That means that 5, that's the derivative of 5x, is equal to secant squared y, and because it's y, we put in y prime. So that means that y prime is equal to 5 over secant squared y. And what we know is that since secant squared y is equal to tan squared y plus 1, that's just another form of the secant squared tangent squared identity, we can replace this with 5 over tan squared y plus 1. We know that tan y is 5x, so tan squared y is just 25 squared x. So that gives us y prime equals 5 over 25x squared plus 1, and that's the derivative.